Welcome to the elementary synthetic geometry-based introduction into inversion of the real plane with respect to a circle course, episode 2, lecture 2, in which we will cover the motivation of this geometric transformation, all the relevant definitions that will equip us with the tools to study inversion of the real plane with respect to a circle, and the corresponding terminology. In order to ease our way into and motivate the study of inversion of the real plane with respect to a circle, let us use something that is very straightforward to imagine and something that requires very little specialized mathematical knowledge to comprehend. A ball on a table. That is, as a thought experiment, let us pretend that on top of a level table represented by this here book, we put a ball and we let that ball rattle around the table a little bit, wait for the ball to come to a complete stop, and now we're looking at a ball that rests on a table, which means that neither the ball is moving with respect to the table, neither the table is moving with respect to the ball. More technically, let us agree that a physical table in our thought experiment is a model of a mathematical object known as a plane. We will name that plane with the lowercase p and we'll represent that plane partially as this funny looking quadrilateral shown in white over here, delineated with straight lines. And let us agree that a physical ball is a model of yet another mathematical object known as a rigid sphere, designated with the name sigma and shown over here in white. Moreover, the fact that our ball rests on a table is modeled in our mathematical experiment by the fact that the plane P is tangent to the sphere sigma at a point S, and conversely, the sphere sigma is tangent to the plane P also at one and the same point S, and we will agree to refer to the point S as the south pole of the sphere sigma. What we want to do now is come up with a way to topologically correlate all the points that make up the sphere sigma with all the points that make up the plane P. And a way in which this can be done is as follows. Through this point S, shown over here in blue, we construct a straight line named L that is perpendicular. This is the sign for perpendicular. So the straight line L that passes through the point S is perpendicular to the plane P that lies below like this, and it is evident that that straight line L will intersect our sphere sigma at two distinct points. The first such intersection point between the straight line L and the sphere sigma will be the familiar to us point S, the south pole of the sphere sigma. The second such distinct point will be the point that sits diametrically opposite to the point S on the sphere sigma. We will refer to this point as N, and it will be the north pole of the sphere sigma. Now we take some amount of mathematical glue. We glue or fix our sphere sigma to the plane P. Then we carefully climb on top of the sphere, position ourselves at the point N, and emanating from the point N, we shine a laser light on the plane P that is logically positioned below the sphere sigma. In this case, what interesting things will happen? Well, two interesting things will happen. Our laser light that emanates from the point N will intersect the sphere sigma at a point to which we will refer as A, shown in red over here, and the ray of light will keep running and it will intersect the plane P at a point to which we will refer as A prime, and then that ray of light will keep running into infinity on its happy and merry way. What this contraption that we constructed over here in a few minutes in grown-up mathematics is called the Riemann sphere, and the point A prime is known as the stereographic projection of the point A. Now, if we patiently move our laser light that emanates from the point N and shines on the plane P down below, up and down, for example, up like this and down like this, and at the same time we make one complete revolution while swinging our laser light up and down about the point N or about the straight line L shown over here, then technically with all the A prime like points we will paint the entire plane P below, and with the A like points we will paint or touch, topologically speaking, almost all the points on the Riemann sphere sigma, and conversely. In the previous segment, we correlated, or as mathematicians would say, topologically mapped almost all the A-like points that make up the Riemann sphere named sigma to all the points that make up our plane P down below. By doing so, we constructed the so-called, and so far, the stereographic projection of almost the entire sphere, not just the stereographic projection of one point onto the plane P below, but of almost the entire Riemann sphere named sigma. And in plain English, in an intuitive way, by doing so, we manage to unfold somehow in an interesting way the sphere sigma onto the underlying plane P below. But if we think about it, then we will realize that nothing can prevent us from carrying out that same experiment, but in the opposite direction, or in reverse order, if you will. That is, nothing can prevent us from climbing down the Riemann sphere named sigma onto the underlying plane P, and nothing can prevent us from literally roaming the entire plane P, and while doing so, shining a laser light that emanates from a representative A prime like point that belongs to the plane P directly at the north pole of the Riemann sphere named sigma. And in this case, what interesting things will happen? Well, again, the interesting thing that will happen is as follows. The ray of light that emanates from the A prime-like point that belongs to the plane P will intersect, again, our fixed Riemann sphere at two distinct points. And putting the cart in front of the horse a little bit, that is precisely the crux of the coming up problem. The first such distinct point will be the red point A, shown over here, and the second such distinct point will be the north pole of the Riemann sphere named sigma itself. And again, it should be fairly evident that if we conduct this experiment by visiting literally all the points that make up the plane P, we will, in some sense, if you will, paint the entire plane P below the Riemann sphere sigma, and by doing so we will mark, if you will, or touch or paint, again, almost all A-like points that make up the Riemann sphere named sigma. And the interesting question now is the following. Why, when we refer to all the A-like points that make up the Riemann sphere named sigma, we keep carefully splicing in the qualifier almost? The reason why we keep splicing the word almost when we discuss the A-like points that make up the Riemann sphere named sigma is because under the stereographic projection of that sphere onto the underlying plane P, as we define right now, the north pole of the Riemann sphere named sigma cannot have a genuine stereographic image or a genuine stereographic projection in the plane P below, and we will give two plausible explanations of why. First, if we're still conducting our experiment in the opposite direction and we're standing on the plane P at the point A prime, then it should be fairly evident that no matter how finitely far away the representative point A prime in the plane P is far away from the south pole S of the Riemann sphere named sigma, the point A will always be distinct from the point N. In other words, symbolically, we can say that as things are set up right now, the point A will always be distinct from the point N, or our representative point A under the corresponding stereographic projection of the Riemann sphere will be distinct from the north pole of that sphere. And here where comes the notion, which in some sense was designed for the layer of mathematics to which we refer as topology. For example, in college, when you will be studying the continuity of a function at a point in the course of, let's say, real analysis, then to some extent that notion of continuity, it may be intuitive, but it may also feel a little contrived in the sense of why do we need it? Well, the study of topology brings the notion of continuity front and center. And remember this, when we manipulate our representative point A prime in the plane P in such a way that we produce its image, which is the point A that belongs to the Riemann sphere sigma, we want the journey of the point A prime in the plane P to be continuous. In other words, we want to paint or touch or visit all the points of the plane P without exception. And at the same time, we want the point A, the representative point A, that happily lives on the Riemann sphere named sigma, to paint or travel or touch all the points of that sphere continuously. So as the way in which things stand right now, the only possibility that we have to continuously roll the point A into the point N, roll the point A into the point N, the north pole of the Riemann sphere sigma, is as follows. We unbuckle our laser light, the source of the laser light, from the point A prime, and in some sense we split our point A prime into two distinct copies. One such copy we keep on the plane P, and the other such copy, which we will name the point D, we lift and we'll let that point D hover above the plane P at the distance that is equal precisely to the distance between the points. Which points? The points S, the south pole, and the points N, the points S and N, the north pole of the Riemann sphere sigma. Sn, and it is evident that that line segment represents a diameter of our Riemann sphere, which is symbolically captured as 2r, where r, uppercase R, is the radius of the Riemann sphere named sigma. And I do not show that point called the center of the Riemann sphere in order to avoid the clutter. We do not need more symbols than we have to have with, but it should be understood that the straight line L that is perpendicular to the point P houses or contains the center, let's say, of the Riemann sphere named sigma. As such, the only technically viable way to continuously roll the point A into the point N, A into N, is to split the point A prime into two copies, keep the point A prime on the point P, lift the second copy of that point named D up into the air, so to speak, and let that point hover above the plane P at the distance that is equal to the diameter or twice the radius of the Riemann sphere sigma. And in that case, the point A will definitely continuously roll into the point N. But here, to be rigorous, we need to introduce another notion, which, because this course is as elementary as it gets, but not less elementary, we will not be dealing with. But for the curious souls, this will be a limiting position of the point A on the sphere as it tends to the north pole end of the sphere. So in this case, we will write something like lim is the symbol for the limit as the point A, tends to the point N, the north pole of our sphere. And in this limit, when A tends to N, the point A gets closer and closer and closer to the north pole of the Riemann sphere N, then our straight line NA, the straight line, let's say the straight line that passes through the points A and N, will become the so-called tangent. Will be a straight line that will actually be tangent, the straight line ND, This will be the straight line N.d, and that straight line will be tangent to the Riemann sphere named sigma at the point N. That will be the line segment, or in this case we can imagine a straight line N.d. That straight line will be parallel to the straight line S.A prime, and it will be parallel to the plane P. But the trouble with this experiment is the following: we are not allowed to leave the confines of the plane P, precisely because the whole point of this ball on a table experiment is to produce a topological correlation or a topological mapping between, ideally, all the points that make up the Riemann sphere named sigma and all the points that make up the plane P. That means that by jumping off that plane, splitting the point A prime into two copies and hovering about the plane P at the distance that is twice the radius of the Riemann sphere, we break that mapping, we break that correlation, and that is not allowed. We still have to operate somehow in terms of being in the plane P and not, that is important, not leaving the confines of the plane P, and conversely. If from the plane P we climb back up on top of the Riemann sphere named sigma and position ourselves at the north pole of that sphere N, then already using the diagram shown on the left side of your screen, we can extract all the actionable mathematics from it right away. Those of our viewers who are comfortable with manipulating mathematical objects in 3 space can do just that, and we recommend that you do that. But in order to make sure that all of our viewers understand what is about to unfold, we will do the following two things. First, we will use the points N, S, and A prime, 3 distinct points, in order to construct a unique plane, because that is how, let's say, the Euclidean geometry works. Any 3 distinct points define a unique plane, N, S, A prime, and with that plane we will cut our ball on the table contraption. That's the thing number one. Thing number two, we either turn that section or cross section so as to make that cross section parallel to the planes of our monitors, or we walk around our contraption that was cut in half and we position ourselves in such a way that we're looking directly at the result of this cross section that is rendered over here on the right side of your screen. That correlation should be easy and straightforward to understand by every person who is watching this episode. That is, our sphere sigma named sigma will be represented when it's cut by the plane that passes through the points N, S, A prime in the 3D rendering, so to speak, of our contraption, with this circle right here, which, in order to eliminate the clutter, the symbolic clutter and confusion, I will also still refer to with the name sigma to underscore the fact that this circle over here relates to the parent Riemann sphere named sigma, and technically that circle sigma shown on the right hand side of your screen is what is called a great circle. This guy right here, great circle, a great circle of the Riemann sphere called sigma. And On that great circle, we have how many interesting points? We have 3 interesting points. The south pole of our Riemann sphere. This is the point S over here in the flattened two-space or two-dimensional rendering of this situation. The point N, the north pole of our Riemann sphere, and this is the point right here. So the point S becomes the point S here. The point N, the north pole, becomes the point N over here. Everything should be straightforward. And the last thing is what? Our point A, that right now sits on the Riemann sphere, on a great circle of the sphere, and that point travels into the point A that still sits on the great circle of our sphere. That much should be understood. The objects that we have in the 3D rendering, if you will, of our ball on the table contraption, that is how they travel into the two-dimensional 2D view of our situation. And lastly, the point A prime that belongs to the point P percolates into our two-dimensional rendering, the cross-section. In which way? Well, this is the point A prime right here. This is the point. And the straight line SA represents what? Well, it represents the side view of the plane. This is the plane that degenerates into the straight line that passes precisely through the points SA. Now let us throw in some more material that will allow us to understand, to grasp what is going on. Over here, the straight line L that is perpendicular to the plane P, the straight line shown over here, is constructed perpendicularly, again, perpendicularly to the plane P, which means that the way things work in Euclidean geometry is that that straight line L will be perpendicular to any straight line that lives in the plane P. The straight line SA prime lives in the plane P. That means that the straight line L that houses the diameter NS of our Riemann sphere is perpendicular to the line segment SA. In other words, the angle NSA prime is what? That angle is right. So that angle is right. Angle is right. That means I recommend that you guys write it down. Technically, the angle NSA prime, the angle NSA prime is right, which also means that the plane of Euclidean triangle NSA prime is also what? Is also right. Wonderful. Next, let us loiter around the point A. That point lives on a great circle of the Riemann sphere, sigma. And that means what? That means that that point is the vertex of the angle in a circumference, because from the point A, what do we see when we look at the points N and S? Precisely, we see the diameter of the Riemann sphere, sigma, or in this case, in our cross-sectional two-space view of that whole contraption, from the point A, when we connect that point with the point N and S, we see precisely a diameter of the circle, great circle sigma. And according to Euclid's Elements, Book 3, Proposition 31, or the so-called Thales' theorem, any circumference angle in any circle is what? Is right. Precisely. So this angle right here is right, and this angle right here is right. But the straight line NA passes also through the point A prime, which means that the angle SA A prime is also what? Is also right. You see? Is also right. That means that this angle right here is also right. Wonderful. How many triangles do we have in this setup over here? Either way, pick your favorite construction. the 3D view or the TD, 2D view, it doesn't really matter. We have precisely three interesting right by construction triangles, which are N, S, A prime, N, A, S, and S, A prime. What is going on with this right by construction triangles? Well, let us make the first observation. All of these three right by construction triangles share one and the same or common interior angle at their respective vertices at N. In other words, this angle right here, this angle, to which we will refer as, let's say, alpha, just for brevity, is shared by how many triangles? Well, it is shared by the triangle NAS and the triangle NSA prime. And in a second, we will see what else is going on here with the third triangle SAA prime, even though technically we do not need that. So we will mark this angle as alpha. Now, by Euclid's Elements, Book 1, Proposition 32, the magnitudes of the interior angles in every non-degenerate plane Euclidean triangle sum to pi radians. That means what? That means that in the right triangle NAS and NSA prime, we have the magnitudes of two angles equal one another. In other words, the angle at the vertex A and AS of this triangle is equal to the magnitude of the angle NSA prime, the right angles. All right angles equal one another. That's, as a matter of fact, one of the basic assumptions that Euclid makes at the beginning of his Elements in Book 1, if I'm not mistaken. And the magnitude of the angle alpha that is shared is one and the same. And what does that mean? Well, that means that the magnitude of the remaining angle in both of these triangles must be one and the same. Let us use the green chalk to mark that angle right here. This angle, to which we will refer as beta, in the triangle NAS will be equal to what magnitude? It will be equal precisely to the magnitude here at the vertex A prime. This will be the angle beta. In the triangle NSA prime. And also, by the way, not that we will actually need it, but this is a side observation that we all should make, that in the remaining third triangle, SAA prime, if this is the right angle, this is the right angle, this is the angle beta, this is the angle beta, what is the magnitude of the angle ASA prime? This guy right here, what is this? Definitely yes, this is also angle alpha. But for now, we do not need that. This is actually what we're doing right now, is we're rediscovering Euclid's Elements, Book 3, Proposition 8, if I'm not mistaken. Basically, in that proposition, Euclid shows that if we construct a straight line that emanates from the right angle vertex of a right triangle onto the corresponding hypotenuse, then all three triangles are actually similar. Similar by what? By A, angle, angle, angle. But for us, we need these two triangles that are shown here, NAS and NSA prime. These two triangles are similar by AAA, by angle, angle, angle. And again, do not worry, in the corresponding chapter, the free PDF file, the link to that file is in the comment section. You can catch all the material that I explain over here. In my book, I spell out all these angles here. I will not do that because it is evident what is going on, even though you guys can go in parallel and trail along and do that. Now, because the right by construction triangles NAS and NSA prime are similar, by the corresponding Euclid's Elements book 6, proposition 4, if I'm not mistaken, the lengths of the sides about equal angles in such triangles are in the same proportion. And which proportion and which distance we are looking for? Well, we want to work with this distance, NA. Remember our point or bone of contention, if you will, the fact that the point A is always distinct from the point N. And now we're sitting on top of the Riemann sphere at the point N, and we're looking down at the underlying plane P, catching the point A prime and A in our laser-like view. So the length of the side AN, let's write it down here, AN, is in the same proportion, and that side AN lies against opposite angle beta, relates to the length of the side AS from the triangle NAS, is in the same proportion as what? Which side in the triangle NSA prime lies against angle beta, which is the same by magnitude as this angle right here? Well, it's the side SN. And what is the side SN? The length of the side SN is 2R, precisely. So we write down SN divided by what? By the side that lies AS, the side that lies against what angle? The angle alpha. And which side in the triangle NSA prime lies against the shared angle alpha? Evidently, that is the side SA prime. SA prime. From here, it follows what? We now want to extract the length of this line segment AN. It is equal to, we carry this distance over here, AS times SN. The distance SN is 2R. Let's write it down explicitly. 2R divided by the distance between the points, which ones? A prime and S. So far, so good. But now we conduct the following experiment. From the fixed point S, we let the point A prime run away as far as it wants to, but the distance S A prime will be finite no matter how large. And in that case, the point A evidently will keep traversing the circular arc, and it will want to hug and kiss the point and get closer and closer to it. In that case, when the point A gets very, very close to the point N, what can we say about the distance from the point A to the point S? What can we say? Well, definitely in this case, when the point A tends to the point N, then the distance AS will be definitely larger than R. Would you agree? Where R is the radius of our circle sigma, which is the radius of our Riemann sphere sigma. Evidently, the distance from the point A to the point S will definitely, most definitely be larger than the radius of that sphere and circle R. And if we multiply this inequality with this material over here, 2R over A prime S, what will we have? We will have that the distance AN from the point A to the point N will be larger than what? 2R times R, which is 2R squared divided by the distance between the points A prime and S. Now, this is what mathematicians do when they want to work with the theoretical material without diving into the official device that mathematicians invented, and it took them about, well, depending on how you look at it, either 150 years or more than 2,000 years, called the limit, because the art of computing limits is the art of manipulating inequalities, and this is what we love. This is what we love when we deal with limits. We love strict inequalities, and this inequality is definitely strict. And how can we read this inequality over here? Well, as the point A gets arbitrarily close to the point N, the point A prime gets arbitrarily far away from the point S. But as long as, again, we stay within the confines of finite distances, no matter how far the point A prime from the point S, which means no matter how large that distance is, this magnitude over here on the right-hand side of this inequality will be what? This is 2, a strictly positive real number. In a non-trivial case, evidently, if r is 0, there is the Riemann sphere degenerates into a point. Nothing interesting going on, even though sometimes collapsing a sphere into a point or a circle into a point is a viable tactical maneuver, but we will take it that r is strictly larger than 0. Square of a real number is always will be greater than 0. The product will be always greater than 0. The bottom line is that this number will always be strictly greater than 0, no matter how small this distance gets. And that hopefully demonstrates the fact that as long as we are within the confines of the plane P, which we have to be for our topological mapping of the points that make up one object to the points that make up the other object to work and be legitimate without breaking any connections, without jumping off the plane P or jumping off the Riemann sphere sigma, we see that under the stereographic projection, the point N, the north pole of the Riemann sphere, cannot have a genuine stereographic image. And how do we resolve this problem? In order to patch things up and extend the set of points on the Riemann sphere that do have a genuine image under the stereographic projection of that sphere onto the underlying plane, mathematicians introduce a single, and it is important to understand that in other scenarios there may be multiple such points, but in this case mathematicians introduce a single, what's called point at infinity. In most modern texts on, let's say, complex analysis, that point is designated with just an infinity like so, but in this course we do not need to be that cruel. We will designate that point at infinity as, let's say, like so, P for point, and infinity as a subscript. So these two symbols will represent a single point at infinity. For now, in this course, we will do the introduction of that single point at infinity mostly formally. We will not dwell on it. We will not develop that subject because, for the most part, at the introductory level, we do not need that. And our viewers who are new to the notion of point at infinity will take their time to reconcile this notion in their mind, because it is not really that particularly straightforward. Here is why. The point at infinity can be thought of in a vague way as an object that is smudged in the plane P in all directions that either emanate from or terminate at the south pole of the Riemann sphere S. And our plane P that is equipped with the single point at infinity technically stops being the Euclidean plane, and it now becomes the so-called extended plane. But once we introduce that point at infinity, then it is taken that the genuine, at this point, image of the north pole of the Riemann sphere named sigma under the corresponding stereographic projection is precisely the point at infinity, which we designate as shown on the right hand side of your screen. And in the opposite direction, it becomes possible to render the point at infinity that is somehow smudged in all the possible directions around the point S in the extended now plane P with precisely the north pole of the Riemann sphere. And in other words, if we simply look on the plane and operate in terms as shown over here, it is really difficult to grasp where exactly that single point is. Well, in some sense, it can be anywhere we want it to be. But once we step up from the plane into the or onto the Riemann sphere, then that point becomes single again, single point and the single north pole of the Riemann sphere, where we name that sphere as sigma. And again, we will not delve too deep into the idea of the point at infinity, even though it plays a very important role in complex analysis. It pays to dwell on it and understand it. For example, if we take our great circle, if we position the coordinate axis in the complex plane accordingly, this way, for example, we'll run the real axis, this way we'll run into the plane, into the board will run the imaginary axis, and then we simply take our great circle that sits along the real axis, we unbuckle it, and that great circle of the Riemann sphere becomes the real axis. Then we can use this as a so-called branch cut, and we use all these ideas of a cut plane to do, for example, contour integration in the complex plane, but we do not need that. One way to grasp the idea of the point at infinity at the somewhat intuitive and not too rigorous, not too formal, but fairly close and faithful way at the middle or high school level is the following. Let's play a game. You give me a real number, strictly, let's say, positive real number. In the interesting cases, rho. It's a real number. It's always greater than 0, and it can be any magnitude. It's as large as you want it to be. You give this number to me, and you tell me, okay, where is the point at infinity? Well, I bring you to the point S, So let's say we use again the same color chalk. This is our point S. And I use your number, your real number rho that you gave me, strictly positive real number, to construct a circle in the parent plane, P, that has the point S as its center, and that has the distance rho as its radius. And I tell you that the point at infinity, this guy, is located strictly outside that circle. And because this circle runs all the way around the point S, let's pretend that this is a circle that runs all the way around. That point can be anywhere we need it to be. But the important thing to understand here is that the point at infinity, symbolized over here, is located strictly outside of that circle. Later on, you come up to me and say, hey, Roman, the number that I gave you just before, no good, too small. Here is another number, twice as large. That's another real strictly positive number rho that is twice as large. I say, okay, come up close to the point S. We will use this point as the center of yet another circle that we construct like so. And that distance over here will also be rho, twice as large. Guess what? The point at infinity, symbolized right here, lives anywhere we need it to be, but strictly outside that circle. And we can keep playing that game for as long as you have patience. You double your number, or you make that number 10 times larger, 100 times larger, million times larger, gazillion times larger. It doesn't matter. I do the same thing. I bring you close to the point S, then we walk all the way to the point rho. We construct another circle. The radius of that circle is still rho, the number that you gave me, and I tell you that the point P lives strictly outside, not in, not on, but strictly outside that circle that has the point S as the center and rho as the radius. And that is how that story rolls onward. But now, again, like I said, we will not be diving deep into the notion of the point at infinity, but it is helpful to have at least some idea of what that point in infinity is, where does it come from, how we can take it from this vague idea of the point being smudged across the parent plane in all the directions that emanate from or terminate at the point S, and boom, have a nice, crisp, single point image of that point as the North Pole of the Riemann sphere sigma, and that point at infinity will figure into our definition of inversion of the real plane with respect to a circle, which is coming up next. Observe that the introduction of the single point at infinity that you saw a few seconds ago in the previous segment on the right-hand side of your screen closes the topological hole, so to speak, and makes our correspondence or the mapping of the points that belong and form the Riemann sphere named sigma to the points that form the underlying plane be a one-to-one correspondence, which is known as a bijection. The mathematicians call this type of a mapping or this type of a correspondence a bijection, and that means that at this point, again, with the introduction of the point at infinity as a genuine image of the North Pole of the Riemann sphere sigma under the corresponding stereographic projection, ensures that every point, now at this point, every point of the Riemann sphere sigma has two things going for it. It has an image, it has a stereographic image in the corresponding plane, and every such point is an image of some point that belongs to the underlying plane P. So this is a mapping that works, so to speak, both ways. Now stepping up closer and closing the circle, so to speak, tying all these things together. Remember that the overall motive of our discussion was taking a very straightforward concept of a ball on a table and looking for a topological way to map the points that form one object into the points that form another object. So now we bring this idea closer together by observing this. Very straightforward, we're going to carry out a very straightforward manipulation. We will use the North Pole of the Riemann sphere, as the center of yet another sphere that has the radius that is equal to 2 radiuses of the Riemann sphere sigma. In order to not clutter our discussion with too many symbols, otherwise we'll just drown in the symbols, I will refer to that sphere as 2R sphere, because that sphere shown over here outside, it runs like this. This is the sphere. It has 2R as its radius and the point N, the North Pole of the Riemann sphere, as its center. So far, so good. So we construct that sphere, let's say, in 3 space. We envision, I do not have the room, but hopefully you envision that sphere. That sphere still touches the plane P, and the plane P still touches that larger sphere at the point S, the south pole of the Riemann sphere, and now the south pole of our larger 2R sphere. Everything is going on the same. We cut all this beautiful mess with the same plane. We turn it around or walk the other way. This is what we see in the plane. So the 2D rendition of this 3-space beauty should be straightforward. Everything is in the same place. Nothing really changed with respect to our material that we developed further. Everything is still the same. But now, in the previous segments, what did we work with when we showed that in the original, perhaps naive way of dealing with the so-called finite plane? Sometimes this plane literally, of course, is infinite. It runs in all directions. But for example, in some complex analysis texts, this is called a finite plane, which is a plane without the point at infinity. But now that the point is at infinity is thrown in there, that plane becomes infinite. Then what is happening with the points A and A prime when we show that under these conditions, when the point A gets closer to N in this naive finite plane way, there is no genuine stereographic image of the point N of the North Pole of the Riemann sphere in the underlying plane. What did we work with? Well, we worked with the sides. Remember, we worked with the sides of these right triangles that actually form the corresponding right angles. In the triangle NAS, we worked with the sides AN and AS. And in the triangle NSA prime, we worked with the sides NS and SA prime. Now we use the same similarity of the same triangles, but instead of working with the sides of the triangles, we bring in the hypotenuses. So now from the triangle NAS, we want to grab the distance NA and its hypotenuse, the distance NS, and in the right by construction triangle NSA prime, we want to grab what? The old side NS, but now we want to pick the distance NA prime, the distance between the points N and A prime, or the hypotenuse of that larger triangle. These triangles are still similar by the same book 6, proposition 4. The lengths of the sides about equal angles are in the same proportion when the corresponding sides lie against or opposite equal angles, yada yada. We know the drill. So let's write down this proportion. In the triangle NAS, we're going to grab the distance NA, related to the distance NANS, the distance NS. What will this be equal to as a ratio in the similar triangle NSA prime? Well, that is straightforward to construct. In the triangle NAS, the side NA lies opposite which angle? Angle beta. So in the triangle NSA prime, which side lies against the angle beta? NS, exactly. So this is what we relate. NS, and we divide it by what? The hypotenuse of the smaller triangle NAS lies opposite what? The right angle right here, right angle at A. And which side of the larger triangle NSA prime lies opposite the corresponding right angle? Well, this is the hypotenuse NA prime. It is this guy against the right angle. Remember, we go back to over here. This is the right angle right here. NSA prime. Wonderful. So this will be divided by the distance NA prime. What does follow from this relation? Well, it follows that the product of the distances, now let's bring these two guys together. You see, the points N, A prime are what is called collinear. they belong or sit on one and the same straight line. So the distance NA times the distance NA prime is equal to what? It is equal to ns squared, but the distance ns is what? Is twice the radius of our favorite Riemann sphere named sigma, so this will be what? 4r squared. Now, if we purely formally, without putting much reading, much mathematical heft into it, designate the distance 2r, let's say under the designation 2r is equal to r, simply one nice short symbol r, then what will this be? Well, this will become r squared, where r is the radius of the 2r sphere that is constructed with the north pole of the Riemann sphere and as the center, and the diameter of the Riemann sphere as its radius. So remember this little relation. This will be the workhorse for the rest of this course. We will come back to this relation time and time again. And the reason I brought this to your attention is because now, with respect to the 2r sphere centered at N with the radius 2r, the point A prime is called the image of the point A. And that transformation is known as inversion of the space, 3 space, with respect to the 2r sphere. And what does that mean? That means that it is possible to interpret the stereographic projection or the transformation of stereographic projection of the Riemann sphere onto the underlying plane P also as the inversion of the space under an appropriately chosen sphere, and that appropriately chosen sphere is what? Is a sphere that has the north pole N of the Riemann sphere as the center, and the diameter of that Riemann sphere as its radius. So that is the connection between the stereographic projection and inversion of the space or the 3 space with respect to a sphere. Now, this is probably a little bit too much, and do not worry if these ideas are vague. By the time we're done with this course, you will grasp this firmly. But, and again, recall that in the previous episode, in episode 1, lecture 1 of this course, I mentioned that in the final episode 29 of this course, I will talk about from here. The inversion of the space with respect to a sphere will be the next thing, and you will recognize that the plane P that is tangent to the 2r sphere under the inversion of the space with respect to that sphere with positive power, boom, will be crumbled precisely into the Riemann sphere. And conversely, any sphere that passes through the center of inversion like this, contained this way, will be unfolded into the plane that is tangent to the parent 2r sphere. Everything works out beautifully, but we do not need that right now. We will reduce our scope a lot. We will forget about this 3 space situation. We will live strictly inside of the plane. This will be our plane, the planar view. But I hope that this introduction makes it at least somewhat more tangible and makes the motivation of the transformation that we will study in this course more evident and more perhaps easier, more straightforward to grasp. And before we move on to the official definition of inversion of the real space with respect to a circle in a few seconds, the takeaway from this situation over here is what? Remember, the stereographic projection with the point at infinity added to the set of points that have a genuine stereographic image becomes what? A bijection. That also means that our inversion also is a bijection. This is where the point at infinity will come in handy. That's number one. Number two, we have the following observations that we will carry into the next segment in a few seconds. The center of the 2R sphere N and the point A form array that contains or houses, if you will, the image point A prime. The observation number one. Observation number two, pay attention to this line segment over here, SA. You see the straight line SA is perpendicular to the ray NA. As a hint, I do not want to spoil this too much for you guys. I want to have the pleasure of making this discovery for you on your own. You will keep it, you will have it, but remember this, you will need this in problem one that is coming up. That's the second observation. And what is the third observation and the final observation? The final observation is that the straight line that is perpendicular to the radius of our inversion sphere NS, which is SA prime, it runs perpendicular to it, right? Marks precisely the spot where the ray NA intersects with that straight line and marks the spot for the image point. And now with this motivation in place, we can define exactly what this transformation is, to which we refer as inversion of the real plane with respect to a circle. With all the ducks in a row, we can give the following official, formal, and rigorous enough definition of inversion of the real plane with respect to a circle. That is, let us agree that for the duration of this course, inversion of the ambient plane P with respect to a circle named C that has the point O as its center and R as its radius will be such a transformation of the plane P into itself, under which every point A of the plane P is taken into a point A prime in a way that honors the following three conditions named C1, C2, and C3. The condition number one, C1, demands that the points O, A, and A prime belong to one and the same straight line or are collinear. I gave a fancy name to that straight line, lambda, precisely in order to impress upon the minds of our viewers that the points O, A, and A prime must be collinear. This is captured with this string of symbols. This symbol here means belongs to. That's the first part of condition one. The second condition of the part one is still important. You should not drop it on the floor cold turkey, but you should remember that we also demand that the circle C, with respect to which the plane is being inverted, and the straight line lambda that houses all 3 points O, A, and A prime are coplanar and belong to the parent plane P. In other words, in plain English, without getting too pedantic about it, what that means is that all the objects of interest, the plane, the point O, the point A, the point A prime, the straight line, the circle, everything belongs to one and the same plane. The condition named C2 demands that neither the point A nor the point A prime is the point O or the mentioned before point at infinity, and this is where your understanding of what point at infinity is comes in handy, and that is why I introduced you guys to that point in the prior segments. That means that the point A is not the point O, and it is not the point at infinity, and the point A prime is not O and is not the point at infinity. And lastly, the final condition named C3, shown over here, demands that the product of the distances from the point O to the point A and from the point O to the point A prime, this distance times this distance is equal to precisely the square of the radius of the circle with respect to which the plane P is being inverted. And in some sense, it is really quite amazing how much hefty, interesting, deep, and meaningful mathematics can be extracted from this one relationship. Books and books can be written on that subject, and a lot of interesting, deep, and hefty material simply pours out of that one little relation. Under these conditions and with that definition of inversion of the plane P with respect to a circle C on the books, we have the following terminology. The circle C is called the circle of inversion of the plane blah blah blah. The point O is called the center of inversion. The radius here R is called the radius of inversion. The radius of inversion. And the square of that radius, r squared, is called the power of inversion of the plane P with respect to the circle C that has O as its center and R as its radius. And with this nifty little string of symbols, C open paren, O comma R close paren, let us designate the circle of inversion because we will be referring to it a lot when we will be proving theorems. This will be our go-to symbolization of all this graphical and visual mess. Now, when I define the inversion of the plane P with respect to the circle C as the transformation of the plane into itself, right now, we're actually, remember, with condition 2, we demand that the points A and A prime are distinct from the center of inversion. We now know the official name for the point O, and we should start getting used to this official terminology. So our points A and A prime are to be distinct from the center of inversion and the point in infinity. So we cannot claim this. That definition means that the inversion of the plane defined as we defined it over here is a bijection, but we want to make it a bijection, and we will precisely by introducing what happens to the center of inversion under the inversion of the plane with respect to a circle. The technical wrinkle that we should consider first is the following. The power of inversion, which is the square of the radius of inversion, comes in two distinct flavors: the positive power of inversion and the negative power of inversion. And these flavors of the type of the power of inversion are defined as follows. By our next definition, the power of inversion of the parent plane P with respect to the circle named C that has O as its center and R as its radius is called positive, shown in blue over here, positive, if and only if the abbreviation IFF reads as if and only if the points A and A prime are located on the same side of the center of inversion O as shown over here. Both points are located on the same side of the center of inversion. And the power of inversion of the plane P with respect to the circle C that has O as its center and R as its radius is called negative, shown in red over here, if and only if the center of inversion O, is located in between in the David Hilbert's axioms of geometry sense, where he puts it as one of the in-betweenness axioms, the points A and A prime. And that means that if the point, the center of inversion is in between the point A and A prime, then the power inversion is negative. And conversely, if the power of inversion is negative, then the center of inversion is located in between the points A and A prime. The same deal applies to the positive power of inversion. If the power of inversion is positive, then the points A and A prime are located on the same side of the center of inversion. And conversely, if in our travels it so happens that we discover that the points A and A prime are located on the same side of the center of inversion, then the power of that inversion was positive. Now, with these definitions of the book we can look at what happens to the center of inversion under the inversion of the plane with respect to a circle. For the duration of this course, let us agree that under the inversion of the real plane with respect to a circle with any power, positive or negative, the center of inversion O is taken into the point at infinity, and conversely, the point at infinity is taken into the center of inversion O. And with this addition on the books, the way we defined inversion of the real plane with respect to a circle becomes what? It becomes a bijection. That means that every point of the parent plane, even the center and even the point at infinity, technically that will be the extended plane, P, has two things going for it. Every such point has an image under the inversion with respect to a circle, and every such point is an image of some point in the plane P. And again, just to be sure, in general, to be perhaps more rigorous than we have to be, the positive power of inversion can be rendered as follows: plus r square or just r square. And the negative power of inversion can be rendered as symbolically as negative or minus r squared, negative r squared. Negative power inversion, positive r squared is positive power of inversion. We will not be doing much, and in my book I do not rely on these symbols too much. We will treat the powers of inversion verbally. If the power is positive, I will just say it, positive power, and if the power is negative, I'll just say it, negative. I will not be shuffling too many symbols, but again, to be perfectly pedantic, perhaps up front, and not be pedantic any further, if the power of inversion is positive, then the center of inversion is taken into the point at infinity, and conversely, the point at infinity is taken into the center of inversion. Likewise, if the power of inversion is negative, then still the center of inversion is taken into the point at infinity, and the point at infinity is taken into the center of inversion. Remember that the way we introduce the point at infinity, it is a single one. It is just one point. Evidently, every circle has one point O. Everything converges nicely together. We have a beautiful bijection of the extended plane. And before we move on, let us briefly discuss the common terminology. The reason why it is a good idea for you to learn this terminology and become comfortable with it is because that terminology is used elsewhere in grown-up mathematics, because that terminology travels well and far. That is, under the inversion of the plane with respect to a circle, the point A, shown over here, for example, has an official name. It is called the pre-image. The corresponding point A prime is either called officially the inverse image of the point A under the inversion of the plane with respect to a circle, and on and on and on. You already know the drill. Or quite quickly, once you understand what is going on and enough disambiguating context is established, then it very quickly becomes, the point A prime becomes simply the inverse. Game over. Now, next. This long and cumbersome to pronounce, cumbersome to write down, but technically just and faithful representation of what is going on, inversion of the real plane with respect to a circle that has the point O as its center and R as its radius. All this long, cumbersome, but technically accurate mess is very quickly compressed into inversion in a circle. Here the word in comes in very quickly, very helpful. So this compresses all this technically accurate but long and cumbersome mess into inversion in a circle. And again, you have to be really careful and know the audience, because it is entirely possible to embed our circle, let's say, or the plane into the ambient 3 space and then try to invert the space. But usually it is evident that the inversion is carried out with respect to the inversion of the plane. All this other mess is dropped and this phrase becomes inversion in a circle or just inversion. That's it. And that's how the name inversive geometry in the real plane comes about. Now, another way to name or phrase these things is the following. I do not want to overload this initial discussion with too many technical details, but it turns out that topologically, straight lines and circles are actually equivalent. And with our point at infinity on the books, now that we more or less understand, maybe we do not grasp all the depth of this idea, but we more or less are familiar with the notion of point at infinity, it is possible to define a straight line as precisely a circle that passes through the point at infinity. And at that point, no pun intended, it becomes virtually impossible to distinguish a circle from a straight line. That is why the terminology, the next one, pay attention to this, reflection, comes into play, because maybe in your middle or high school travels you are familiar with the geometric transformation called reflection in a straight line. We can have a couple interesting symmetries. They are also called symmetry in a single point, or reflection in a point, and symmetry in a straight line, or reflection in a straight line. So here, once we understand that a straight line can be actually defined as a circle that passes through the point at infinity, it is very well possible, and it is completely legitimate to use the word reflection of the real plane with respect to a circle, yada yada. You know all this technically correct but cumbersome drill quickly collapses the whole thing into reflection in a circle. Game over. Reflection in a circle. This is a synonym for this long, cumbersome but technically accurate phrase. Now, the final terminology I want to make sure that we all agree on hails in some sense from the beautiful study of the theory of groups. And even if you are in middle school or in high school, you should not be afraid to take on the initial study, the introductory study to the theory of groups. I have a free book available in the same repository. Poke around, you will find it, a bunch of free PDF files. Download, read in parallel, study my introduction, let's say, to the theory of groups and the introduction to inversive geometry in parallel. It will benefit you in both directions. But in the spirit of the theory of groups, again, this long and cumbersome phrase actually compressed very quickly too into this phrase, symmetry in a circle. Now, this takes us a little bit away, lifts us off the ground and this immediate intimacy with exactly what's going on. The word symmetry can have several different interpretations, but still the word, when you hear the phrase symmetry in a circle, symmetry in a circle, you can pretty much rest assured that this is yet another terminological synonym for this long, technically accurate but cumbersome phrase, inversion of the real plane with respect to a circle, blah, blah, blah. You know the drill. Now, if you have any questions, by all means, the comment section is open. Do ask. I hope that I covered all the bases. If anything is not clear or confusing, then ask a question. Either I myself or I hope maybe someone from our community will step forward to help you out. And this is almost it for episode 2, lecture 2. The next short segment will be only for those of our viewers who do not think that they know the difference between a circle and a disk. The final segment of episode 2, lecture 2 is optional. It is addressed only to those of our viewers who think that they do not fully understand or are confused by the fact that a circle is not a disk and a disk is not a circle. And granted, it is perfectly fine to be confused by these two notions because especially in the context of middle school and or high school, there do exist perhaps legitimate situations where the two objects, a circle and a disk, can be used interchangeably without deep diving into the nitty-gritty details. But in grown-up mathematics, these two objects are actually very different, and here is why. A circle depicted on the left side of your screen is actually a closed planar curve, each point of which is located precisely and exactly at one and the same fixed distance from a special fixed point called the center of the circle that is located in the same plane in which the curve itself is located. Now, that point, the special fixed point, is called the center of the circle, and that fixed, given ahead of time, technically non-negative real number, and usually in the interesting case, a strictly positive real number, is called the radius of the circle. From that definition of the circle, it follows that as a mathematical object, a circle is a one-dimensional object precisely because the position or the location of any point P on a given circle can be completely described or can be completely captured with one real number called theta, which is the angular displacement of that point with respect to an arbitrarily chosen axis and measured in the agreed upon direction. That is, the radius of such a circle is known. It is a fixed number. It does not vary. It stays one and the same. So this is not that bit of information cannot vary. It is fixed. So the only uncertainty, if you will, about the location of the point P on a circle is its angular displacement. And where is it? By knowing what is the angular displacement, boom, we can find the exact location of that point once we settle on all sorts of pesky details. Now, in contrast, a disk shown in the middle of your screen is a planar region. It's not a closed planar curve, but it's a planar region, each point P of which is located not further away from a special fixed point called the center of the disk than a given ahead of time fixed, again in a non-trivial case, positive real number. That positive fixed and given ahead of time real number is called the radius of the disk. The point from which we measure the actually linear displacement of all the points that belong to a disk is called the center of the disk. And from that definition, it follows that a disk is actually a two-dimensional, not one-dimensional object like a circle, but a disk is a two-dimensional object. And why is that? Well, because the precise location of each and every point that belongs to the disk can be completely captured with how many real numbers? With two real numbers now. The same angular displacement as in the circle case with respect to an arbitrarily chosen axis and measured in the agreed upon direction. Plus, we need the second real number to fix the location of such a point, which is what? Which is now a linear, or we can call a radial, but to be more technically accurate, a linear displacement of that point from precisely the center of the disk. Thus, two real numbers, theta and rho, in order to fix the location of every point in the disk, two-dimensional object. That is the big and fundamental difference. A two-dimensional object, a one-dimensional object. A circle is not a disk, and a disk is not a circle. Analytically, in a traditional, properly chosen Artesian coordinate system, an origin-centered circle can be rendered with our favorite x squared plus y squared equal. That is why I put the equal sign in red, because this sign is of significance, equal to r squared. That means that the point that technically belongs to a circle is not located inside, is not located outside, but is precisely on the circle. And sometimes we can say the words on the periphery of the circle or on the circumference of the circle. But that is the important bit of information here in the analytical representation of an origin-centered circle with an equal sign. Now, here comes another big difference between a circle and a disk. An analytical representation of, let's say, origin-centered disk already varies depending on a property of a disk that is not available for a circle. And that property can be called the closure, even though the word closure has its own specific and precise rigorous meaning in mathematics, but for the lack of better word. And what does that mean? That means that unlike a circle, a disk, well, it can come in many different flavors, but two very popular, but not the only flavors of a disk are an open disk and a closed disk. You see, in general, in grown-up mathematics, we will not say that a circle is open or closed. A circle is just that, a circle. But a disk can be open and it can be closed. If a given disk is open, then its analytic representation for the origin-centered, yada yada, is captured with the strict inequality sign over here. Again, I showed it in red, strictly less than. That is the important bit. If, however, a given disk is closed, then its analytic representation for the origin-centered, yada yada, is used with the less than or equal to r squared. See, feel the difference between the two. Now, just about the only case that I can think of, if you guys can think of any other case, use the comment section and educate me on the matters. But the only case when the two objects become indistinguishable, when the radii of both things converge into zero and both of these objects become a single geometric point. And that is a valid tactical maneuver. Sometimes it actually helps us solve problems when we can look at triangles that have vertices as points, but in reality, these points used to be circles before. We blow these points into circles, and then voila, we have some tangency, maybe some seconds, and some beautiful things can happen. But fundamentally, right now, this is what we need to grasp. A disk is not a circle, and a circle is not a disk. Now, in the study of topology, a precise meaning to the word that I'm about to use is given. We will not delve into this. There is no need for this. Otherwise, again, we will drown in all our favorite universal quantifiers for all and for each. The existential quantifier exists. We do not need to do this. This is just a basic intuitive understanding. We can think of, for the purposes of this course, that a circle is a boundary. This is the magic word, the boundary. A circle is, give or take, the boundary of a disk, and conversely, a disk is the innards of a circle. Again, give or take, there are all sorts of nuances involved and lots of fine print once we get into the nitty-gritty, which we do not need to get into in this course. In plain English, at an intuitive level, a circle is a boundary of a disk, and conversely, a disk is the inner portion, inner region of a circle. Again, give or take. Mathematicians in the audience know what I am talking about and should cut me some slack for not diving into all these details here. We do not need that. And a similar analogy exists when the things come to a sphere and a ball. Again, a sphere is not a ball, and a ball is not a sphere. An analytic representation of a sphere uses precisely, again, this is origin-centered sphere, constructed with respect to a Cartesian coordinate system, but here we use the equality, the equal sign. That means that the points that belong to a sphere, they do not belong to innards of the sphere, they do not belong to outward region, they are precisely that distance away from the center of that sphere. With the ball, however, the things are different. Again, we understand that we can take the ball to be open, this is one property, or for that ball to be closed. And if such a ball is open, then its analytic representation for origin-centered, on and on, uses the strict inequality, strictly less than sign, as shown over here in red. And if a ball is closed, then the similar analytic representation uses the less than or equal to. This is of significance. And again, in plain English, at the intuitive level, we can think of a sphere as a boundary of a ball, and conversely, a ball is the inner portion of a sphere, give or take. Once we get into the grown-up topological definitions, things will change. And as a matter of fact, in topology, putting the cart in front of the horse a little bit, in topology, the definition of the boundary is not given right away. First, the way these things done in grown-up mathematics is usually this is the workhorse. This turns out to be the workhorse of the definition around which everything is built. This will be called the neighborhood of the point. Then for the neighborhood, we define the points that are exterior, the points that are interior, and then and only then, after giving all sorts of wonderful definitions, we come to the idea of what the boundary is. And still, that definition is slippery. It confuses a lot of students, invariably all the time. Pretty much a lot of students are confused. What is a boundary? How can we wrap our brain around this? If for any exists such that, how we can wrap our brain around it. Again, we do not need to dive into this. For the purposes of this course, it is enough to understand that a circle is a boundary of a disk, and the disk is the inner portion of a circle, give or take. And it is important to have a clear mental image of exactly what are we studying the inversion of the plane with respect to. Remember, the name of this course is an elementary synthetic geometry based introduction into inversion of the plane with respect to what? With respect to a circle. And this is what is the main character, one of the main characters of this course, a circle, not a disk. A circle is not a disk. Now, again, if you guys have any questions, if anything is still confusing or something is not clear to you, please by all means use the comment section to this video. The comment section is open, but this is it for episode 2, lecture 2. And starting with the next lecture, we'll begin studying how exactly our inversion that we defined in the previous segment with respect to a circle acts on the points. We'll start with the points. We will look at what happens when such a point sits precisely on the circle of inversion. Then we will see what happens if the point that we are acting on with the inversion of the plane with respect to the circle is inside, and what happens to the point if such a point lives outside of the circle of inversion. And we will hash this over the positive and negative powers, so you might as well start thinking about what will happen in these three interesting cases. And I will see you in episode 3, lecture 3 of the elementary synthetic geometry based introduction into inversion of the real plane with respect to a circle.